Hi everyone, we want to create a device called Bili, and we'll explain it in the presentation. Yes.
Yeah, so the kind of thing that we wanted to diagnose is hyperbilirubinemia, which is when there's high levels of bilirubin in the blood. So there are two types of bilirubin that we're going to discuss, which is the unconjugated and the conjugated forms. The type that we care about is unconjugated bilirubin, which can cause brain damage. And as you can see on the slide, 60% of full-term babies and 80% of preemies have hyperbilirubinemia. And it has a 10% mortality rate, but also a 70% long-term morbidity rate. Next slide. So we just did a quick by the numbers and just found that approximately 670,000 babies need treatment, and that would be 55,000-ish a month, and also like 390,000 babies per month have long-term complications due to this. So there are a couple existing devices that we looked at. The ones that we kind of wanted to target were the jaundice detector, so TCB measurement device, which is like a light-based measurement device. It's not invasive and is mostly it shines a light onto certain portions of skin and then measures the different wavelengths that it reflects. And then the other type would be microfluidic tape paper, which its main drawback is that it doesn't differentiate conjugated and unconjugated. And then also the downside of the spectroscopy version is that it could have trouble with darker skin pigments. So the limitations that we want to address, cost. So the ECB measurement device is pretty expensive, and we also wanted to address measurement of types of bilirubin. So we want to measure only unconjugated, and then we also wanted something that doesn't use electronics, so doesn't need to be charged or anything like that. And next. And we wanted something that could be both qualitative and quantitative, so something that can be it can diagnose jaundice qualitatively, but if we wanted to be more thorough with it, we can add quantitative methods to it.
So you can use it in a triage setting, but you can also
Yeah.
give out an
So the first design we had was similar to the TCB measurement device, but we wanted to go a little bit more frugal with it. So we have this. So here's our kind of like light path diagram. So we have a light source that focuses down to a beam and it bounces off the skin. And in order to display the results, we wanted to use a prism that splits all the wavelengths of colors. It can either use artificial light or sunlight. And see all of that. And then it would display onto panchromatic paper, which is essentially the same kind of like paper or like film that's used for black and white film. So we found that you can actually make a pretty cheap beam splitter using just two glass slides that are separated from each other, and that's just a photo of it working. And we found that we had trouble reflecting enough light off of skin using Frugal methods. So we pivoted to look into a design that would shine light through blood, but found that the issue with this is that shining light through blood with unconjugated bilirubin will actually convert it into bilirubin, the conjugated version, which is what we don't want to measure. And we also found that there may be some issues for just visually detecting it by just shining light off of a prism. So if we're going to shine it onto panchromatic paper, we found that, so this is kind of like what a light spectrum would look like, but if we're just shining it off of skin, it would look something like this, but then skin with jaundice will look something like this, and you'll notice that like it's very hard to like discern the data as something that we would just
With a
like.
human
visually
readout
see.
rather than adding cat.
Yeah.
Mm.
Yeah, so this is just kind of a summary of like all the problems with like the light-based approach that we went for.
Okay, so instead of doing that, we transitioned to a more chemistry-based approach. And so the first issue that we had to tackle was isolating the blood plasma, which is like the liquid part of the blood, because that's where the bilirubin will be. And so the key functionalities we wanted to have was to use as little blood as possible, because you can really only get about 100 microliters from a baby. And then we want to be able to separate plasma, isolate unconjugated bilirubin, and then eventually detect it. So the first phase of our device was blood collection. We saw that there was a glass capillary method that is used sometimes in practice, where they would take advantage of capillary action to draw blood. So we tried to do the same thing, cutting the end off of a transfer pipette, but it didn't really work. We kind of moved on though, because this wasn't the most important part of our thing.
I think glass and plastic, huge contact angle.
Yeah.
Mm.
Mm.
Yeah. So then we wanted to be able to separate plasma from the blood. And so there were a bunch of methods that we tried using. One of them, or a lot of them were paper-based. So we had these filter Wattman papers, and we were also kind of taking advantage of capillary action. We were hoping that the plasma would diffuse through the paper while the red blood cells would be inhibited. And then there were a bunch of different methods that we found in literature. And one thing that we found to work was salting the paper, which makes all the blood cells get smaller and packed together. And they kind of move around as bigger units, and that also frees up plasma with more space. We also used a handy fuge, which he has there, and we saw a lot of success with that. So with 20 microliters of blood, we were able to get about 10 microliters of plasma.
I never talked about it, so most people don't know what that is. Yeah, keep going.
So the first thing we tried was using a syringe filter, but we think the pores are actually too small, and that kind of blocks plasma from getting out. So we got red foam out, which shows that blood cells are actually getting through. Yeah, this is a video of the centrifuge method working. So we were able to get what we needed from this, and that's a picture of the result. And then we also tried different types of cellulose paper. So Wattman paper is a lot less absorbent than transblot paper. And so we found that you got a nicer spread, which is kind of what we were looking for. And then this is just a video of our salted paper. And it's kind of hard to tell from this picture,
Yeah.
like on the projector, but the
edges are different.
and the paper that we had salt on had a lighter color, which was indicating that it was more plasma and less RBCs. And so we tried a bunch of different concentrations of salt, and we found that if you put too much salt, it actually we don't get as good results. So we found around 1 molar salt was about right for us.
So now the plasma is actually transferring from one layer to the other layer.
Correct.
Mhm.
And
Without the blood cells being.
Yeah, so our results were not quite what we saw in papers because we didn't have the same Wattman paper, but we're pretty confident that once we get this, we'd be able to get these kinds of
So this is
results.
what another paper did, and you can see it's pretty easy to get the plasma to separate. So we figured this wasn't like a huge point of issue in our steps.
Why is it not? Oh,
Okay, so the third phase is now we want to finally isolate the unconjugated bilirubin because that's the deadly stuff or the stuff that can cause issues. And so we thought, can we take advantage of what makes the unconjugated so deadly? Because it's water insoluble, meaning it will not be urinated out. So that means because it's water insoluble, it binds super tightly to albumin. And in fact, in 1969, it was really hard to even know the KD of it because it binds so tightly. And in recent years, they found, wait, can you go back?
Sorry.
In recent years, well, not recent years, but like 10 years later, they finally found that the binding, the KD was 30 nanomolar, which is like super small. Like usually you want something on the micromolar scale. So then we went back to some old papers and we used the principles of Bradford, I'd say, to bind albumin, which will then immobilize the unconjugated bilirubin. And with
You're
some,
gonna use albumin separated out.
sorry.
You're gonna use albumin will be the stationary phase.
Yes, exactly. We immobilize albumin, which is bound to the unconjugated bilirubin. And so we did some tests with CBB, which just binds, it's a broad spectrum protein binder, but it also binds albumin. And you can see that it's kind of hard to tell, but there is a color change between 0 mg per mil and 80 mg per mil of BSA, which is just albumin. So we wanted this to be a little more visual. So we then turned to a different formulation of CBB. And the original formulation used phosphoric acid because once you proteinate the CBB, it has this characteristic color. And you can see that when you add increasing levels of BSA and plasma, you have this color change. And it was enough for us to make a calibration curve and then also measure how much plasma comes from blood. And we got 80 mg per mil, which is physiologically relevant. This is some failures. So we found with our other CBB formulations, it worked kind of nicely when you microwave it to heat it onto the Whatman paper to kind of fix it on the Whatman paper. So we tried to do that with this new formulation, but that was definitely the wrong move because we started burning it. And then I have a quick demo. So I have CBB paper.
Who's gonna donate the blood?
Well,
We already have a syringe. Why is it doing the demo? It's supposed to be a puzzle for to figure out how to operate. There's no portion in it, no matter how much full it's not. That be loading. It's the initial step. Once you've loaded it, you have to play with what frequency you're going to pull to keep injecting the energy. So that's what we have to break that. Okay. When early on it's starting, you want to make sure that there is. This is what we want. And then does this one take Eppendorf tube?
yeah.
So which is kind of nice because then the Eppendorf tube is double sealed, which helps a lot. It's still one. It's not good.
Design it to take PCR tubes, so.
So you can see I'm letting it coil because if I was not timing it correctly, I would be. So take a few minutes to get started. So you build inertia in it. Now I can put the frequency. So the question is, what frequency would you come to? Okay, let's do the demo.
Really quick demo of new CBB formulation. And I'll kind of just drop some plasma on. You can see that. Yeah, it turns this bluish purplish color. But yeah. So because they have a colorimetric reading, we can also build our calibration. Oh, I already said that. Okay, cool. Yeah. Maybe I can pass this around. Actually, no, this is plasma. So.
I already heard that. Yes.
The next part we want to detect bilirubin. Now that we immobilized it. So basically, first we need to wash away anything that was just absorbed on the Whatman paper because in that Whatman paper it was plasma, so it has also the conjugated form. So if you just wash that away with water, you can wash that off. And then now you want to unbind the unconjugated bilirubin from the albumin. And some really old papers have shown that you can use some chemicals like this methyl p-hydroxybenzoate, but I've also read some other papers that you could probably use ethanol. It's just not to the same extent. Then it came to the issue, how do we wash this? Because we want this to be a colorimetric assay that's like pretty easy to use. and we decided on these ketchup designs. So our first version was just putting water in like this type of tape, was it?
It's just
Electrical tape. And then our second version was having like this cutout because we want it to be more directed. Because you can see in the first version, you have to push really hard and then it kind of squirts everywhere. It kind of got on Alex's computer too. But when you have this cut design, it kind of has like, it kind of breaks a little easier. Next. And then finally, once you wash away the unconjugated onto a second piece of paper, that second piece of paper will ideally have the chemicals to then have that colorimetric readout for the bilirubin. And people have done diazo, which is pretty cheap, but we also found this other cool method of this chloric acid. Unfortunately, we didn't get our diazo strips in time, so we couldn't test that. But
Even the urine test, it's on the way.
so cost of one device, when we laid everything out, the biggest cost will come from the plasma separation paper or the Wattman paper, whatever we use. And the other stuff that's more important for like binding the unconjugated and actually detecting it. It's a upfront, it's a big investment. But when you do the per cost,
That upfront doesn't really matter.
yeah, because
You're doing hundreds of millions of tests.
yeah, for example, for the CBV with 50 grams, you can make 3 million tests. Which is just like a crazy amount just from 50 grams.
Okay, so after we thought of all of these, we were kind of thinking about how we could package this to ship it out. And so we were thinking about these folding designs that would kind of help put the different stages together. And then we would have the ketchup packets in each of these leaflets so that you could do the washing steps. And then we would use some kind of film to protect things from making contact before they were meant to. And then on the other side would probably be some like absorbent papers and stuff like that. So I guess we can just pass out. We came up with 3 versions of them.
Okay.
Sure. The one that we eventually ended up thinking was most feasible was this booklet method, where there would be 3 pages. The first one would be plasma isolation. The second one would be unconjugated bilirubin isolation, and then the final one would test for the bilirubin levels. So yeah, this is kind of how it works, where you would go from left to right, flip the pages, and it would have instructions on like where to press to initiate each of the steps. And then we wanted to do like a way to quantify it. So we figured out how to make an iPhone app, and like basically you can either like take a picture from your phone or just take a picture of the test, and then you find where the circle is, and you will have a calibration curve preloaded in here, or like in the case that you're in different like different environment, you can tune the parameters yourself. So there's like a screen in here to basically take different known values, you just do the same thing, and then it will make the calibration curve for you. So the next steps for this would be to get a hold of diazo, which is kind of the core. Yeah, we ordered it, or that one.
Just get the data.
Okay, we haven't put that in yet. Okay.
Yeah, and then
You guys are so close, it's important to test.
Mhm.
Then you know the pipeline works.
Yeah.
And then another very important thing will be testing how well the washing steps work, because we want to make sure that we're really isolating what we think we are. And yeah, we want to test other plasma methods.
Ideas on washing, we can talk about that separate. You want to wash, but you also want to capture it.
Yeah. So
It's the opposite way is much easier to do. When you wash away a component that you don't care about, it's stationary. But when it has to be a wash with a minimum amount,
yeah.
it really has to be a jet that you then so as a spot.
Yeah. There's a thought like maybe having a third packet, that's the diazo reagents that you then just squirt on a third piece of layer, and then you just bring it into contact with the CBV paper.
Capturing what you want.
Yeah, this is just some random
Everything we try.
Time for just one quick question. One quick question.
Everything?
Let's talk about how long it takes. The
Uh,
last 2 weeks.
yeah.
Amazing.
It was last second, we were like, because our lab, CBB is super popular,
Yeah.
but our lab somehow doesn't have it. We use something else called Ponsu, so it doesn't have a color shift. So we were like desperately asking in our building Slack for CBB and Wattman paper, and then we got it, and then that was like everything over the weekend. And then also getting blood, I had to like beg my lab mate to let me use some of the, not his blood, own blood, but like he got blood from like a lab that he then isolated and he had to use neutrophils for, but I had to like beg
We
him
had
for
tested
materials.
blood.
Yeah, okay.
That's good. It all worked out.
Mhm.
Okay, let's switch.